Hi, my name is Joe Sinkowitz, and I work for NOAA at the Ocean Prediction Center, where we're responsible for marine weather warnings and forecasts for both the North Atlantic and the North Pacific. So I'm going to talk today about maritime weather from 36,000 kilometers above the Earth's surface. In other words, from geostationary satellites, and talk about the utilization and limitations of satellite data to the marine forecasting problem. So what's changed over the last couple of years? We're kind of in an evolution that short-term decision-making can now be better done using satellite imagery. And part of the rationale or the reasons for that are the rapid availability to forecasters of the data. In other words, a reduced data latency, that we're no longer getting data that's 20 minutes old, 40 minutes old, where a storm system, thunderstorms complex, convection complex, existed and then has faded. We can visualize, for a variety of different reasons, I'll go into that in the next slide, time rate of change of the atmosphere. Data acquisition of the data is relevant. It requires minimal interpretation. A lot of decisions went into deciding what channels, what bands to sense the Earth's surface and all. And the last one is that forecasters are trained on the capabilities, and that's really critical. That way they're not trying to learn on the fly, but are actually trained and have expectations in how to use data. Also, the next step is basically artificial intelligence and designing and developing tools that then can be used with forecasters to start at a higher level in the decision process. And as an example of some of the advancements, down in the lower right is a target area over a intensifying tropical cyclone in the western North Pacific, and at 2.5-minute imagery, a visible image. And actually, I think it's a visible image. And you can see basically the detail and actually see how the storm is changing. So what has changed? It really is about the imager. Basically, for the Himawari satellite, it's called AHI. And for the geostationary GOES series of satellites, it's ABI, Advanced Baseline Imager. And the resolution is much higher for all of the channels that have been in the past, for all the capabilities, whether it be visible, infrared, or water vapor, which in essence is an infrared, both in the horizontal resolution, but in the case of the infrared, in the vertical. There are many more channels, or also called bands. And it allows for the development of products using multiple channels. And here are the list of a number of channels that are focused in different areas: visible, near infrared, and infrared. And the Himawari capability and the GOES-R capability are quite similar, because in essence they're the same imager with just some slight differences, and you can see the differences there. I've also included links in this. So the Himawari and GOES-R, if you're curious, there are pages that are linked right there that you can go to and learn a lot about what the capabilities are. The temporal sampling has changed. For full disk now, they're both GOES and Himawari are producing images every 10 minutes. GOES over the United States is at 5-minute, where Himawari over Japan is at 2.5 minutes. And they also have a target area, which is what I showed in the first slide, of 2.5 minutes, and landmark areas of 30 seconds. On the US side, we have mesosectors, which are 1 minute, and 2.5, which is the target area, is 2.5 for Himawari. The limited latency to ground system and distribution is absolutely critical. So in other words, the data is fresh, it's new, and it's relevant, and that's really critical and a game changer. No longer waiting for data like we used to in terms of anyway. So latency, reducing the latency means you're making decisions on nearly real-time data. So I'm going to give one example of, on the US side, of something we're working on. It's called Prob Severe Lightning Cast, or LC. And it was developed at the Cooperative Institute for Meteorological Satellite Studies at the University of Wisconsin, and uses geostationary lightning mapper data, another instrument on the the GO series of satellites. It is an imager, and the field that it's using is flash extent density. So it's designed to predict lightning out to 1 hour, and it is proving itself to be useful for offshore thunderstorms in a probabilistic sense. And the example here shows basic contours and probabilities of lightning occurring within the next hour. So the potential uses beyond US Doppler radar network, such as in the offshore waters. And if you think about it, lightning is a proxy for convection for high winds, waves, and possibly reduced visibility and high rain. It is neural network based, machine learning trained from both imagery. It matches the textures and picture values, but also to the global lightning mapper flash density within the next hour. So there's a growing use of geostationary imagery and products for short-term forecast decisions. It's facilitated or buoyed by satellite capabilities and reduced data latency. It doesn't solve all the challenges. Fog and reduced visibility still is a challenge, especially when there is a high-level cloud masking the low cloud, and also determining whether a stratus cloud or is fog. Thunderstorm detection, yes, but the associated conditions remain challenging. And it does reveal the complexity of the fluid of the atmosphere and ocean, and in some ways can make interpretation and resulting decisions more challenging, but we're all learning together. Thank you very much.